Hello, welcome to episode 5 of Maths in an Empty Classroom with me, Mr. Southern. Today we're going to be looking at the second example of statics of rigid bodies. So if you haven't watched the first one, you need to go back and watch the first one before you look at this one. Here we go. Right, so a uniform plank AB of length 6A and mass 25m rests in equilibrium in a vertical plane with the end A on rough horizontal ground. So, recalling keywords: rough, there's going to be some friction at the point A. A small stone of mass 3m is attached to the plank at B. The plank is resting on a small, smooth, horizontal peg C, so no friction at C, where BC equals 2A. The plank is in equilibrium, making an angle alpha with the horizontal, where sine alpha equals 3/5. The coefficient of friction between the plank and the ground is mu, unknown, and the plank is modelled as a uniform rod lying in a vertical plane perpendicular to the peg, and the stone as a particle. Okay, wonderful. Right, so we've got a copy of the diagram there, but what I've actually done is just got a bigger version here so that we can label what's going on. So we were told first of all that this was a uniform rod, so I can draw a point at the centre, because if a rod is uniform, the weight will act at the centre, and we have a force of 25 mg acting down, which is the weight of the rod. We know that the whole length of the rod is 6A, so what I'm just going to do is another one there, because what I need to indicate there is that the distance there is half of that, it's 3A, because this is a uniform rod and it's therefore halfway. I can see that I've got a distance 2A here, so I'm just going to split that bit of my length into A, 2A, to show that overall I've got the 6A, and then I can use those lengths later as and when I need to. I've also got a smooth ball B, which had mass 3m, so I'm going to put 3 mg there. And as I've been mentioning throughout these videos, because I've got a force that's not acting perpendicular to the slope, I'm going to draw in lines that are perpendicular to the slope. Well, let's just make that actually look perpendicular. Inevitable. There we go. Because I know that the angle in here is going to be the same as the angle here, which I've been told is alpha, where sine alpha equals 3/5. Now I know that if sine alpha is 3/5, cos alpha is going to be 4/5. If you're not sure where that comes from, watch the video on connected particles and inclined planes. I explain how to get that. Okay. Right, other forces acting on the system. Let's just review the wording of the question and what we labelled. We said that there was rough horizontal ground at the point A. So, a couple of things are going to be happening at A. First of all, A is in contact with the ground, which means that we're going to have a reaction force A acting vertically upwards, so we'll call that reaction A. And because it's rough, we're going to have a frictional force. And again, let's think about what way friction's going. Well, if the rod wants to slip that way and move that way, friction must be going the other way. So we're going to draw friction in as going in this direction here. Label that with lowercase f. We've also got a reaction force at the point C here. and we're going to have a, and we'll draw on there a vertical line. Again, I know like drawing vertical lines at the moment. There we go. And that angle in there is going to be alpha as well. Okay. Now, why am I not drawing in a reaction force for the ball here? Well, the reason that I'm not doing that is because the reaction force on the ball from the plank is not affecting the system. It's not affecting the plank. That is a reaction force between the ball and the plank, which I will not have to consider when I'm resolving my forces. Right, let's review again what it is that we are working on. So we've got mass 25m, small stone of mass 3 and attached at B, smooth horizontal peg at C where BC equals 2A, and we've dealt with that, and at the moment we don't know the coefficient of friction. Okay. So the first thing that we're being asked is to find the magnitude of the force exerted by the plank on the peg in terms of mg. So, here we go. So the force that the plank exerts on the peg will be the same as the force that the peg exerts on the plank. So what this is actually asking me to do is to find the reaction at C. Now, remember we've got 3 options of things we can do with these questions. We can resolve vertically, we can resolve horizontally, and we can do moments. Now, with this one, I'm trying to find the reaction at C. I'm going to take moments, and I'm going to take moments about A for the same reason as before, is that if I take moments about the point A, I can ignore the reaction at A, and I can ignore the friction at A, 2 forces I don't know. By taking moments about that point, I can ignore them both. So, moments about A, I know it's going to be in equilibrium, so clockwise equals anti-clockwise. Now, first of all then, let's think anything that's wanting to make the rod go clockwise. Well, first of all, I've got this 25 mg force here. But I need to consider what is the horizontal distance between 25 mg and the point where I'm pivoting. So I need this length here, which is going to be 3a, which is the distance identified there, times by cos alpha. So 25 mg times by 3a cos alpha is going to be the moment created by this force here. Similarly, going around, I have another force here, 3 mg, which is going to make the rod want to go clockwise about A. So I have 3 mg multiplied by, now this one is 6a cos alpha, because the hypotenuse of that is the whole 6a. So 6a cos alpha, and that is going to equal anything that's trying to make it go anti-clockwise, which is just the reaction at C times by 4a. Now, by labelling my diagram with the lengths earlier on, I know that that is the distance there. So RC times by 4a. So, what that allows me to do is I've actually got 75 mg A cos alpha here, and I've got 18 mg A cos alpha here, which equals 4a times by RC. So the first thing I'm going to do before I do any more calculations is I'm going to cancel all those a's. So a A. And I can do that because I'm cancelling it off all of the terms. I then see that, look, I've got 75 mg cos alpha, I've got 18 mg cos alpha, so I can collect that together, which gives me 93 mg cos alpha equals 4 RC. Now, I know that cos alpha is 4/5, so I'm going to put in 93 mg times by 4/5 is 4 RC. 4/5 of 93 is 74.4. So 74.4 mg equals 4 RC. Then dividing by 4, I get that the reaction at C is 18.6 mg. And that is part A done. Okay. So, part B then, what's part B asking me? Find the least possible value of mu. Now, the least possible value of mu, we've got the situation here where the plank is in equilibrium, which means the forces are balanced, which means it's actually on the point of moving, which means that friction must be at its maximum. So if mu was any bigger, there'd be too much friction, it wouldn't be on the point of moving. It doesn't really matter in the context of what we're actually going to do, but that's the explanation of why it says least possible. What we are just going to do is we're going to find the friction at the point A, we're going to find the reaction at the point A, and we're going to